Hello guys, welcome back to another sections of chapter 4. So now we're moving on to section 3, length and orthogonalities. All right, so here's a few homework questions that you can try. All right, so here's the definition of the length again. So we talked about the magnitude in section 4.1 before, but now we'll focus on the inner product space of that. So suppose we have u and v to be vectors in an inner product space, then the length or the norm of u is the same thing as magnitude of u, which is the square root of the inner product space, which is square root of u1 times u1 plus u2 times u2 plus dot 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 and so on. And u and v are orthogonal when the inner product space between u and v equal to 0. So this is similar to the dot product concept, right? So recall in section 4.1, u dot v equal to 0, then u is orthogonal to v, okay? Or similar to that. So, there's a similarity between the inner product space versus the dot product, but it doesn't mean they are the same, right? In dot product, it's just dot products. It's just one item, but this here is considered as the entire space. So you can see like that. All right. So here is how we define. Suppose we have three vectors, p, q, and r, and define their inner products of two functions as the dot product. So we're using a dot product to define the inner product space in this case. And you can see how we find PQ and QR. We did that in the previous exercise. You can see here in the previous section, that's what we did, right? So we did find PQ and PR. It's the same thing. The only thing that you kind of see here, add on to that is find the magnitude of Q. So the magnitude of Q is equal to the inner product between Q and Q, square root of that, according to this definition. Yes, the length is equal to that. So it's equal to the inner product space between Q, and then take the square root of that. So so this equal to the inner product space between 4 minus 2s, 2x, I mean, and then 4 minus 2x. So this gives us 4 times 4 plus with minus 2 times minus 2. So we get 16 plus with 4, give us radical 20. So that's the magnitude of Q. Or you can write 2 radical 5. It's the same thing. All right. Yeah, very straightforward on that. Yeah, that's all about 4.3, length and orthogonalities. Well, now 4.4 is kind of neat the concept of 4.3. So orthonormal basis, right? Orthonormal basis. There's a few things and a few definitions. So be very careful with each definition itself. And here's some homework for you to try. Go ahead and do those. And let's revisit unit vectors as we mentioned in section 4.1. Unit vectors is, technically any vector in Rn can be 5 unit vectors. A unit vector is a vector that have length 1. So if we define u as a unit vector, so u will be v divided by the magnitude of v. All right, u we consider to be the unit vectors. So here's the example. So v equals 3, -1, and 2. Find the unit vector of v. So yeah, so let's find the magnitude of v first. The magnitude of v equal to the inner product between v and v, square root of that. So this one we have 3, -1, and 2, and then 3, -1, and 2. So this gives us 3 times 3 plus -1 times -1 plus 2 times 2. So this gives us 27 plus 1 plus 4. So that's 32. All right, so therefore the unit vector, which is v divided by magnitude of v, equal to 3, -1, and 2 divided by radical 32. So this gives us 3 over radical 32, comma, 1 over radical 32, and then 2 over radical 32, just like that. All right, so why is that important, right? Because next we're gonna focus on orthogonal and orthonormal basics. Those two are different things, right? Orthogonal and then orthonormal. Those two are different things. All right, so let's see what is orthogonal first. So a set B of vectors in an inner product space V is called orthogonal when every pair of vector in P are orthogonal. So again, what does that mean by orthogonal? So orthogonal when the inner product space equal to 0. Okay, so that's the idea of orthogonal. Now, if each of the vector is also a unit vector, then we have ourselves an orthonormal set, right? So remember, orthogonal and orthonormal are different things. You can see here, orthogonal if the inner product space give you 0, orthonormal if the inner product space equal to 0 and the unit vectors and the magnitude of each vector in there equal to 1. So there's two conditions, right? Orthonormal require two. Require this one and this one. Orthogonal only require the first condition, right? They're very, very different from each other. Watch out for those definition carefully. All right, so here is that orthonormal, right? So in order to do orthonormal, you need to check two things. You need to check that and you check that. So you need to check vi vj equal to 0 and the magnitude of each vi equal to 1. So let's check the first one first. All right, so this is v1, v2, and then v3 pretty much. All right, so let's see. All right, so yeah, so v1, v2, this equal to, 1 rad 2, 1 rad 2, comma 0, dotted with negative rad 2 over 6, rad 2 over 6, 2 rad 3 over 6. So there we go. So we get 1 rad 2 times with negative rad 2 over 6 plus with 1 rad 2 times with rad 2 over 6 and plus 0 times 2 rad 3 over 6. And that's give you 0. Okay, next, take v1, v3. So which is 1 rad 2, 1 rad 2, 0, dotted with 2/3 minus 2/3, and then 1/3. So you get 1 rad 2 times 2/3 minus plus 1 rad 2 times minus 2/3 plus 0 times 1/3. So that also is 0. And then v2 and then v3, which is negative rad 2 over 6, rad 2 over 6, and then 2 rad 3 over 6 over 3. And then dotted with 2/3 minus 2/3 and then 1/3. So this gives minus rad 2 over 6 times with 2/3 plus rad 2 over 6 times with minus 2/3 and then plus 2 rad 3 over 3 times 1/3. So this gives us, some cancellation here. You get negative rad 2 over 9 Plot with rest, oh, another minus rest 2 over 9, and then plus 2 rest 3 over 9. So, yeah, so the answer will be 0. Yeah, so the one is good, right? So this one is good. All right, number 2, you're gonna check the magnitude of VI equal to 1. So check the magnitude of V1, which is 1 radical 2 square plus 1 radical 2 square plus 0 square. So this is 1/2 plus 1/2. So that would be 1. Magnitude of V2, which is negative rad 2 over 6 square plus rad 2 over 6 square plus 2 rad 3 over 3 square. So you get 2 over 36 plus 2 over 36 plus with 4 times 3 over 9. So we get 2 over 36 plus 2 over 36 plus 12 over 9. So now you're going to get the LCDs. So now we get, we're getting 4 over 36 plus 12 over 9. So that's the same thing, divide by 4 for the first one. You get 19 plus 12 over 9. So that's 13 over 9. So this doesn't equal to 1. So B is not orthonormal, but it is orthogonal. Okay? It's not orthonormal because it doesn't satisfy 2 conditions, but it's orthogonal because it satisfies the first conditions. That's the idea. Make sense? Okay. Next example. So is a set B orthonormal again? If it's not, can we make it become orthonormal set? All right, so orthonormal, you're gonna check VI, Vj equal to 0, and the magnitude of Vi equal to 1. Check the first one first. Vi, Vj equal to 0. All right, so first you do, this is V1, V2, V3 again. So V1, V2 equal to 1, negative 1, 2. And then 0, 2, 1. I want to check this. This become 1 times 0 plus negative 1 times 2 plus 2 times 1. So we get 0. And then V1, V3. Same thing as 1, negative 1, 2. And then phi 1, negative 2. So this become 1 times phi plus negative 1 times 1 plus 2 times negative 2, also 0. And last but not least, so V2, V3, same thing as 0, 2, 1, phi 1, negative 2. So 0 times phi plus 2 times 1 plus 1 times negative 2. So also 0. Yeah, so that's good. So next, we're gonna check to see if the magnitude of each VI equal to 1. So let's check V1 first. So V1 will be 1, negative 1, 2, and 1, negative 1, 2. So you get 1 times 1 plus negative 1 times negative 1 plus 2 times 2, square root of that. So this gives us 4 and 6, radical 6. And then V2 2, which is 0, 2, 1, 0, 2, 1, which is 0 times 0 plus 2 times 2 plus 1 times 1. So that's 4 plus 1, that's radical 5. And then V3, which is phi 1 negative 2, 1 negative 2. So you get phi times phi plus 1 times 1 plus negative 2 times negative 2. So 25 plus 4 is 29, plus 1 is 30, so radical 30. Okay? So B is not orthonormal because the magnitude of VI does not equal 1. So here's the question is that if it's not orthonormal, can we make it become orthonormal basic set? The answer is yes. We can make it become an orthonormal set when it already an orthogonal set. By finding its unit vectors. All right, so U1 equal to V1 over magnitude of V1, which is 1, negative 1, and 2, divided by radical 5. So you get 1 rad phi, negative 1 rad phi, 2 rad phi. U2 will be V2 divided by magnitude of V2, which is 0 to 1, divided by radical 6. Oh, my bad, this one was radical 6. So now this guy radical 5. So get 0, 2 rad phi, and then 1 rad phi. And then U3, which is V3 over magnitude of V3. So you get phi 1 negative 2 divided by radical 30. So you have phi rad 30, 1 rad 30, negative 2 rad 30. Now, B star, which equal to 1 rad 6, negative 1 rad 6, and 2 rad 6, comma 0, 2 rad phi, and then 1 rad phi, comma phi rad 30, 1 over rad 30, and negative 2 over radical 30. Is an orthonormal set. Okay, so not every set can become an orthonormal set. If the set already become orthogonal, then you can make that orthogonal set become an orthonormal set. Make sense? Okay, so in order to create an orthonormal set, you better verify that it's already orthogonal. Right, so you verify that first. If that's good, then you can make it become an orthonormal set. Does it make sense? Okay, good. All right, so next we take a look at the idea of orthogonal matrix. Okay, what is orthogonal matrix? So a square matrix P is called orthogonal when it's invertible. Right, so when it is invertible and P's inverse must equal to P transpose. So any matrix considered to be orthogonal if and only if it's invertible and P's inverse equal to P transpose. Okay. So first you have to be able to find the inverse first, and then you want to see whether P's inverse equal to P transpose or not, right? For example, you can see here. Let's say we have A equal to 1, 2, 3, and 5, and then A inverse equal to 1 over 5 minus 6, 5, -2, -3, and then 1. So this give us -5, 2, 3, -1. Yeah, so A is invertible. So A is invertible. Okay. Now A transpose will be 1, 3, 2, 5. So now you're gonna check what is A transpose equal to A's inverse or not. So A transpose is 1, 3, 2, 5, and then A transpose is A transpose is 1, 3, 2, 5, and A inverse is -5, 2, 3, -1. So clearly they are not equal. So A is not a orthogonal matrix. Make sense? So that's the definition. That's what it means, right? So it has to be invertible, and this has to be true. All right. So now how can we form an orthogonal matrix? All right. So here's the theorems. An n by n matrix is orthogonal if and only if its column vector form an orthonormal set. So that's bring us back to this one up here. It have to be an orthonormal set. So this 3 up here will not form an orthogonal matrix, but this 3 out here will form an orthogonal matrix. So you can say that, okay, P equal to 1 red 6, -1 red 6, and then 2 red 6, and then 0, 2 red 5, 1 red 5, and 5 over radical 30, 1 over radical 30, and -2 over radical 30 is an orthogonal matrix. Is that clear? All right, so back to that. Okay, so very nice theorem. So it is orthogonal if and only if its column vector form an orthonormal set. So that's what we did up there. So that's the reason we need those up there. All right, so next one. B is if B is an orthonormal basic, then P transpose times P will always give you the identity matrix. Okay, but if B is only an orthogonal basic, then P transpose times P will give you the diagonal matrix. That's the difference. Okay, that's the difference. That's the difference. All right, so go back to this again. So this guy, when I have P equal to 1, -1, 2, 0 to 1, 5, 1, -2 is orthogonal basics, not orthonormal, because P times P transpose will give me the diagonal matrix versus the one down here, this guy. When you do P times P transpose, it will give you the identity matrix. That's the difference. Okay, P transpose times P. Yeah, P transpose times P. P transpose times P. P transpose times P. Very important. P transpose times P. Okay. All right. So I hope that makes sense. All right. So here's the example. Is this matrix orthogonal? So we're gonna use this theorem right here. Then we can do that. Right. So yeah, column vectors from an orthogonal set. Or you can set, well, if P transpose times P equal to identity matrix, then it's orthogonal. So that's what it is. All right. So let's see. So so 0, -1, that's the first column, and 1, 0, that's the second column. So when you do 0, -1 in the product space between that and this, we get 0 times 1 plus -1 times 0. It does give you 0. And the magnitude of 0, -1 equal to 0 plus -1 square. Square root of that, it does give you 1. And the magnitude of 1, 0, which is square root of 1 plus 0 square, that's also give you 1. So P equals 0, -1, 1, 0 is orthogonal matrix. Right, you can check. Let's say, what is P transpose? P transpose will be 0, -1, 1 and 0. So P transpose times P is something as 0, -1, 1 and 0 multiply with 0, 1, -1 and 0. So there you go. So 0 times 0 is 0, 1 times -1 is 1, 0 times 1 is 0, 1 times 0 is 0. So yeah, so this is 0, this is 1. So it does give you the identity matrix. All right. So next example is the matrix A, phi -12, 12, phi is orthogonal matrix. All right, so let's see. We can have, right, when you do this, so when you do A transpose times A, see what you get? So A transpose times A will be phi 12, -12, and then phi times with phi -12, 12, and phi. So let's see, phi times phi is 25, 12 times 12, 144. So we get 169. And then 5 times -12 is, I think, and then 12 times 5. Okay, so this is 0, is 0, and then 169 here. So this one is the diagonal matrix, not the identity matrix. Okay, so it's not, so A is not an orthogonal matrix. So how do we make A become orthogonal matrix? So you can see here when you do phi and then 12 and then inner product space with -12 and then phi, we do get 5 times -12 plus 12 times phi, we do get 0. So it's orthogonal basics. So in order to convert to orthonormal, you need to find the unit vectors. So convert to orthonormal, we need to find unit vectors. All right, so U1 equal to V1 divided by magnitude of V1, which is phi 12 divided by 25 plus 144. So we get 5/12 divided by 13. So we get 5/13 and then 12/13. And then U2 equal V2 divided by magnitude of V2, which is -12/5 divided by 144 plus 25. You get -12/5 divided by radical by 13 again. So you get -12/13 and 5/13. So call that A star equal to 5/13, 12/13, -12/13, and then 5/13 is now orthogonal matrix. So when you check A star transpose times A, you will get the identity matrix. Okay, so the main focus here is orthogonal is not the same thing orthonormal, right? Orthogonal is not the same thing as orthonormal. So just be careful with that. So orthogonal set versus orthogonal matrix is a different thing. Orthogonal matrix when the column vector form an orthonormal set. Okay, watch out for that. That's how you check. All right, so that's it for today, and I will see you on the next 2 sections.